In this lecture, we want to continue our look at iterators. Data structures that have a single parameterized type should always implement the iterable interface. In order to do this, you must add implements iterable to the signature of the class, i.e. public class linked list E implements iterable E. You then add a single method to your class, and that method is called iterator, lowercase I, and it returns an instantiation or a concrete instance of the iterator interface. We want to look at array-based and then linked list-based iterators. First, the iterator helper class should not have a parameterized type because it doesn't have any data of its own. So you want class iterator helper with no parameterized type, implements iterator E. E is the type, of course, from the enclosing class, and therefore you're going to use that type to implement the iterator, but the iterator helper has no data of its own. In general, iterators should not modify anything in the enclosing data structure. The data structure is a linked list, then the iterator should never change that list. If it's an array, the iterator should never make any changes to the array. If the existing structure cannot provide the functionality that's needed, then you need to make a copy of it to get the behavior that you want. For instance, suppose that the enclosing data structure has an unordered array, but the requirement is for an iterator that returns things in sorted order. In that case, it would be wrong to sort the array in the data structure. Rather, you must make a copy of everything in that array and then sort the copy. The copy should be made the same size as the current size or the number of elements in the structure. You do not want to clone the existing array and sort it because you will have null elements in it. Then you want to use the sequence through the array that makes the most sense. That is, if an array holds a stack, then operations happen at the end of the list. You would not, for instance, use push and pop on the front of an array, because to insert at index 0 you would have to shift everything down to make room for it, and then with a pop at index 0 you would have to shift everything down to fill in the hole. Thus, push and pop when operating on the front of an array would be big O of n. However, if you push onto the end of the array and remove from the end of the array, then both operations become big O of 1 instead of big O of n. Thus, it would be wrong to use the front of the array to do this. So when you're doing the iterator for a stack, it makes sense to traverse the array from back to front rather than starting at index 0. If you do it this way, then the elements are returned in the same order that they would come out of the stack with the pop operation. So here's an example to look at. Imagine that the underlying data structure, the array does not keep things in sorted order. However, the iterator must do this. In this case, you must make a new auxiliary array inside the iterator. Load that array by copying the outer or the data structure array, and then you will need to sort it. So here's the beginning of our iterator class, iterator helper. And notice that the iterator helper again does not have a generic type parameter. We have three local or class level variables rather. The iterator index to sequence through the array. We have an array called local array, and then the modification counter to make the iterator fail fast. Notice that we create our new local array. This is the array that exists only in the iterator, not the enclosing class, and we make it current size. We then sequence through and fill our local array from the outer or the enclosing data structure and then sort it. So now we have the same data twice in our data structure, once where it was before in the enclosing structure, and then the second copy of this is in the iterator helper. Here's the rest of the code, which is just the same as other array-based iterators, but we're using local array rather than the storage that we referred to. We referred to the array in the outer class as storage, but here we're using the local array in the iterator class to satisfy those requirements with the next method. The same principle that applies to array-based iterators applies here. That is, you should never change the enclosing class in any way. You should not change the linked list in the same way that you should not change the array where the data is held in the data structure. Use a local variable node pointer to traverse the list and to read the elements in the linked list to satisfy the iterator requirements. If the elements need to be returned in some order rather than head to tail, then you must create an array and fill that array in. Here's the standard approach. We have an iterator pointer, which is a node type pointer. It's initialized to head, and then it's used to sequence down the list to satisfy the iterator requirements. Here's the rest of it. The hasNext method, notice our stopping condition. The iterator is finished when the iterator pointer becomes null. So as we sequence down the list starting at the head, when we get to the end, iterator pointer will become null, and that's the signal or marker that the end of the list has been reached, and so that will be the end of the iterator. In the next method, notice that we must capture the data before we move the iterator pointer down. Once we have moved down, we cannot go back and get the data. Therefore, we assign iterator pointer.data to a temporary variable, move the pointer down, and then return that temporary variable. Here's an example of using an auxiliary array with a linked list. So this is the situation where the order of the linked list is not what's needed for the iterator. In a case like this, you must create an auxiliary array and fill it in. So this is what's happening in the constructor for this list iterator helper. We make a new array of current size and then fill that array in using the traversal of our linked list. The rest of the methods here are exactly the same as they are with array-based iterators, because we're using this auxiliary array inside the iterator class. So using iterators with composition, as we saw in a preceding lecture, it's fairly common to make one data structure out of another. So for instance, if you have a linked list that works well, then you can use that very often to build a stack or a queue. We've seen code like this before. What we want to look at now is the iterator. Sometimes students want to try to get access to the nodes inside the linked list in order to implement an iterator. This is a mistake. You cannot get access to private nodes inside a linked list. Therefore, what you can do, or what you must do, is use the iterator built into the linked list to satisfy the iterator in your queue or your stack or whatever the case might be. In this case, it's as simple as return list.iterator because the order is what we need. In this case, we're looking at a queue. If we have implemented a queue using the linked list, then almost certainly we add to the end of the list and remove from the front of the list. We do this because we can't remove from the tail end of the list. So if we add at the rear and remove from the front, we will have big O of 1 behavior, which is correct. And the first element to be removed when we dequeue will be at the front of the list, so that order would be correct for the iterator. There are times when the order the iterator gives you will not be correct. You need to change it in some fashion. And an example, here we have a priority queue class implementing iterable. It uses a linked list. But for this example, we're saying that the priority queue is not stored in any particular order. That is, when you dequeue, you must find and remove the correct node from the list. But when you add to the list, you just tack it on the end, insert at the rear. So in this case, the priority queue class has an unordered linked list, and the iterator for that linked list is going to return them in an order that would be incorrect for the priority queue. So we need to deal with this behavior. The way you do this is you still use the linked list iterator because there's no other way to get access to the data inside that linked list. But we will use it to build the correct order we need. So since we don't have access to the nodes, we will make an auxiliary array, load that array, and then sort it to get the correct behavior. Here's the constructor. We create a new array, and then we use the enhanced for each loop, which is part of the list iterator. And we use this to load our array. Then we sort it. So now the array can be traversed in the usual way. It returns elements in the priority queue in the same order as the dequeue operations. Here is the rest of the code. Note that rather than using the linked list iterator, we're sequencing through this local array that we built in the constructor and filled in. This concludes our lectures on iterators.